In this presentation, you're going to learn more about the relationship between the nature of light and how it relates to atomic theory. And we need to do this in order to understand how Niels Bohr developed his model of the atom. The first thing that we need to know about is the electromagnetic spectrum. Why do we need to know about it? Because Bohr used it when he was developing his model. You recently completed a web quest where you explored the electromagnetic spectrum, and what you should have learned from that activity is that electromagnetic radiation has both electric and magnetic components, and it ranges from radio waves to gamma rays. When we talk about the electromagnetic spectrum, there's three variables we need to be concerned with. Wavelength. Basically, wavelength is the distance between two peaks that are next to each other on a wave. It's represented with the Greek letter lambda, which looks like a stepladder. The second variable we need to be concerned about is frequency. Frequency represents the number of times a wave appears per second, so the number of oscillations per second. It is measured in hertz, or you might see it sometimes represented in cycles per second, or S-1. The Greek letter that's used to represent frequency is nu. It looks like a V with a tail attached to it. The third variable we need to be concerned about when we're talking about about electromagnetic radiation is velocity. And velocity is how quickly a wave is moving. And what is really important to understand is that all electromagnetic radiation is traveling at the same speed, and that is the speed of light. The speed of light is 3 times 10 to the 8th meters per second. The relationship between velocity of EMR, its frequency, and wavelength is shown with this equation right here. That equation can be written in Greek letters, such as C is equal to lambda nu. Okay, so the speed of light is equal to the wavelength times the frequency. You could also represent it with traditional English alphabet letters with this equation here, where the speed of light is equal to the frequency times the wavelength. What's important to understand is that the higher the frequency the electromagnetic radiation has, the shorter its wavelength. So what that means is the waves are appearing more often because there's less distance in between them. The opposite is also true. If you have lower frequency radiation, it means the wavelength is really long. And how do we know that? Well, or why does that happen? It's because the waves are appearing less often. There's more distance in between their peaks. So what I have done right here is to put the velocity, frequency, and wavelength relationship into a triangle similar to what we used when we were using density. The velocity of, the velocity in meters per second is the speed of light, that's c, and that's a constant, 3 times 10 to the 8th meters per second, is equal to frequency. So frequency is in hertz or cycles per second, which is S-1, and wavelength is in meters. Remember to, when you're using the triangle to help you solve a problem, you cover up the variable that the question is asking you to find, and that leaves you with the formula. So what we're going to do here is a problem example using the relationship on the previous slide. So the question is asking us to find the wavelength of light with a frequency of 65,000 hertz. So the first thing that we need to do is look at what information do we have and what do we have to find. So here's the information from the triangle. So C, speed of light, wavelength, frequency. Okay. So when we look at this, the question is asking us to find the wavelength. So cover wavelength up in the triangle, and you are left with lambda equals c over nu. Okay. Now we can substitute in. C is a constant, 3 times 10 to the 8th. And nu is in the question at 65,000. Okay. And when you say 3 times 10 to the 8th divided by 65,000, you get 4,615 meters. So that's a very long wave. Knowing that, you can refer back to the electromagnetic spectrum slide at the beginning. This is likely some kind of radio wave. So we're going to go through and do another problem example. Okay, this next problem is asking us to find the frequency of some electromagnetic radiation, and it gives us a wavelength of 875 nanometers. So the first thing that you need to pay attention to, remember, is that when you're using the relationship between wavelength, frequency, and velocity, that wavelength needs to be in meters, and this is given to us in nanometers. So metric conversions are going to come into play a bit here. So remember, I did say at the beginning of the year that things that we were learning, we would be continuing to use. So you need to go from nano to the base. So you're moving 1, 2, 3, 4, 5, 6, 7, 8, 9 places to the left with your decimal. So 875 nanometers is equal to 0.12345 875 meters. Okay. At this point, we're actually ready to solve the problem. Remember, to solve the problem, you cover up frequency in the triangle, and that leaves you with the formula. So frequency is equal to the speed of light over the wavelength. So that number gets substituted in the denominator. And when you solve that, you get 3.43 times 10 to the 14th hertz. Okay. The next calculation that we need to have under our belts is an understanding of how to figure out how much energy is associated with electromagnetic radiation. So it would be better, instead of saying given off, to just calculate the energy of electromagnetic radiation. And the relationship is stated here. Energy in joules is equal to Planck's constant. Planck's constant is another value that I would provide you always. And it is 6.63 times 10 to the negative 34th joules per second. The units aren't important, but the value of the constant is. Okay. So energy in joules is equal to Planck's constant times frequency in hertz. So you'll see that formula expressed a couple of ways using traditional English letters of the alphabet, such as this right here. Energy is equal to Planck's constant times frequency, or if you're using Greek letters, energy is equal to Planck's constant times frequency, and remember that frequency is abbreviated with the Greek letter nu. Basically, the higher the frequency of wave, the more energy it has, the more penetrating it is. So this is why you get covered up with a lead apron when we get X-rays, and why gamma rays turned Bruce Banner into the Incredible Hulk. So what we're going to do is go through a couple of problem examples using this relationship. In other words, calculating the energy of electromagnetic radiation. So the first thing that we need to do, remember, is to record our formula. So E equals H nu. Okay. And the question does calculate the energy, and it gives us a frequency, and that actually should be 10 to the 12th. Okay, so 4.5 times 10 to the 12th. So we can substitute in at this point 6.63 times 10 to the negative 34th times 4.5 times 10 to the 12th. And when you solve that, you should get an answer of 2.98 times 10 to the negative 21st joules. Okay, and that's not a ton of energy, or a very small number, in fact, when we're thinking about this. But what you should be paying attention to is that we're talking about small bundles called photons. So this makes sense. Okay. To figure out what kind of electromagnetic radiation it is, we have to find the wavelength of it. So this is going back and using C lambda nu, the triangle that we were using a few minutes ago. And so to find wavelength, remember lambda is equal to C over nu. So we say 3 times 10 to the 8th. And we divide that by our frequency, 4.5 times 10 to the 12th. Okay, and when you do that, you get 6.67 times 10 to the 5th. times 10 to the negative fifth meters. Okay. And I would say that that's likely infrared radiation. All right, so this is our last problem example. And this is a two-step problem because it's asking us to calculate energy, but we're starting with the wavelength. So our first step is to figure out the frequency associated with that wavelength. So remember our relationship C, lambda, nu. So we are looking for frequency. So to find frequency, remember nu is equal to C over lambda. You need to convert nanometers to meters. And remember we found out a few minutes ago that that conversion, that you're moving 9 places left. Okay. So I will just assume that you're understanding the metric conversion part and do the conversion as I'm solving the problem. So 3 times 10 to the 8th is the speed of all electromagnetic radiation travels at. The wavelength is 1, 2, 3, 4, 5, 6, 9, 5, 6. Okay. So the frequency is equal to 3.14 times 10 to the 14th hertz. Okay. Now we're about halfway done the problem. The next thing we need to do is to take that frequency and figure out how much energy is associated with that. And remember, you say E equals H times nu. So 6.63 times 10 to the negative 34th times 3.14 times 10 to the 14th. And when you solve that problem, you get 2.09 times 10 to the negative 19th joules. Small amount of energy associated with it, and again that makes sense because you're talking about a wave. So Bohr used these calculations to develop his model of the atom, and we'll be looking more at Bohr's model of the atom once we're better at these calculations that we've been looking at, because what he did was he used those calculations to help establish the various energy levels within his atom.